So this is chemical thermodynamics, and my opening slide here shows a deck of cards, coins that are randomly flipped, and ink being dispersed. And all this is related to the topic of entropy. Okay? So let me go ahead and talk to you about why thermodynamics is important. It's important because we really want to know when we have a reaction or we have a process, whether that process will even work. And if it doesn't work, maybe we need to invest some energy. Well, how much energy will it cost? So that's the questions that thermodynamics tries to answer. And sometimes process, no matter how hard you try, just won't work. Okay, and we can figure that out based on the laws of thermodynamics. Sometimes process will always work, no matter how hard we try not to make it work. And again, that's addressed by thermodynamics. So this particular slide shows a reaction pathway, and you guys should recognize this particular diagram because we've seen it in kinetics. We have an initial energy, we have a final energy, we might have an activation and barrier here, okay? And it seems like it's a one-step reaction. It could be more complicated than that, but we're trying to simplify it here. Well, the path by which that reaction takes place in going from reactant to product, well, that's kinetics, okay? Kinetics will tell you how long it takes, what the mechanisms might be, but the endpoints, the energy at the beginning and the energy at the end, that's thermodynamics. In fact, what you will see, as you have seen in when we looked at enthalpy in our last lecture, was the products, the enthalpy of the products minus the enthalpy of the reactant, and that gave us the enthalpy of the reaction. So we're just looking at the start and end point. And you guys remember what type of function that is when we're just looking at the start and end point and not looking at the path by which we get there? I remind you that in thermochemistry, we call that a state function. A state function doesn't look at the path by which you get there, it just looks at the endpoint, okay? So this is what we are going to be studying in thermodynamics as far as enthalpy, entropy, and free energy, okay? So the main question, as you saw in my opening scribble there, thermodynamics tries to address, is that process spontaneous or is that process not spontaneous? That's the ultimate question that thermodynamics tries to address, spontaneity. So a lot of things are spontaneous, okay? And we take it for granted. For example, we age. As much as we like to stop aging, we just can't. That's a spontaneous process. It's just a law of nature. Objects falling. Here on planet Earth, objects falls because of the gravitational force. Time always moves forward. Yeah, they say we can slow time down if we are in a plane and we're moving fast. Time will slow down, but it's always moving forward unless someone figures out time travel. The sun rising every day. Okay, we take it for granted that tomorrow, well, this evening the sun will set and tomorrow the sun will rise. That's just a spontaneous process. And if you take an drop of ink and put it in water, as long as it's water soluble, it will disperse and mix with water. That's a spontaneous process. So, and of course, chemistry exams are spontaneous. We don't postpone that. So anyway, spontaneous processes are governed by the law of thermodynamics. We do grow old, things do fall, water freezes at a certain temperature, and time doesn't go backwards, and chemistry exams are not canceled, okay? But you can under certain conditions, under certain process, change the spontaneity. For example, we know that water freezes when the temperature, as long as we're at 1 atmosphere and the temperature is below 0 degrees. But when we raise the temperature, then the water doesn't freeze, it actually melts. So there are certain conditions in which we can change the spontaneity from spontaneous to non-spontaneous, or even reverse it, okay? So that's an important process for us to understand in terms of what conditions can we change the spontaneity, and that's what we're going to see in this particular section. When I was a graduate student in Santa Barbara, okay, we had a seminar, and the guest speaker was Stephen Hawking, and you guys probably know him. He passed away in 2018, but he was had this disease that in which he couldn't speak and he couldn't walk, but his mind still worked brilliantly. Anyway, he was pushing his book, The History of Time, at the brief history of time at that point, and so he was making the circuit. And it was pretty amazing what he was talking about. He gave a 55-minute seminar, and he talked about the Big Bang Theory. Okay, the Big Bang, as you guys know, is how the universe got started. There was nothing, and then it sort of was sudden. We had this Big Bang, and then everything was produced from that. But he went on in his book to say that eventually the universe will stop expanding and it will start contracting because of all the matter and the dark matter that is in the universe. And remember, things tend to collapse upon each other. That's how planets form. And so he called this particular phase the Big Crunch. Anyway, it was pretty amazing, the scenario he provided. He said that, well, perhaps maybe in the Big Crunch, instead of time moving forward, time will reverse itself. We will rise from our graves and die in our mother's womb. Milk spilled will self-organize and go back in the carton, okay? Trees will go back to its seedling and its seed. And he was making all these, he was basically telling us a story about time moving backwards. And then he got a little bit into the math. Said that, yeah, we worked out these equations and everything, and we came up to this one particular part of the equation. And he said that, well, as much as we'd like to think that we can relive and go backwards in time, it won't happen because of the singularity theorem, which breaks down if that were to occur. It's like in the math equation, when you divide something by 0, you know that when you divide something by 0, it's undefined. Can't be, you don't get a solution on that. And so he basically said that when you get to the equation, you get to the singularity, which breaks down if that occurs. But it was pretty fascinating, his take on time and the spontaneity of time and all that. Someone asked him a question at the end of the seminar. It took him about 5 minutes to put that all in his synthesizer. And his answer was pretty brief, probably 1 or 2 sentences, but just goes to show you that his mind was still working and he was really making a big effort to address questions. Anyway, I just wanted to share that with you because, like I said, time moves forward. It's a spontaneous process, unless we figure out, of course, how to time travel. But under certain conditions, we can make a spontaneous process non-spontaneous. We can make a non-spontaneous process spontaneous, okay? And you guys will see how that works when we study thermodynamics. So like I said, this is the history of what happens when I was part of the attendance when Stephen Hawking visited Santa Barbara. This was back in 1988. So it was a good 33 years ago, okay? Anyway, spontaneity is not rate. Remember, rate is addressed by kinetics. It deals with how fast you get to equilibrium. Spontaneity simply address, will that system work or not? And if it doesn't work, do you need to invest energy in order for that thing to work? Okay. So you guys already are familiar with spontaneity. If you take, for example, an ink and you put it in water, it mixes. Or you guys also know that exothermic process, the combustion of fuel, it generates a lot of energy. And so that's a downhill process. You start with a fuel and you end up with a byproduct that is lower in energy. And that difference in energy is released into the surroundings. Okay, that's an exothermic process. Exothermic process, because it's downhill, is generally a spontaneous process. Okay, exothermic process will generate heat. But if you take, say, an exothermic process might be the dissolution of sodium hydroxide. If you take sodium hydroxide pellets, you put it in water, it gets warm pretty fast, exothermic. If you take ammonium chloride, however, these are the same chemicals that you find in CVS. And what you do is it comes in a pouch and you break the seal and it gets very cold. That's an endothermic process. It's absorbing energy from the surroundings. That's why it feels cold to your hand, because it's removing the energy from your hands. That's an endothermic process. And yet the mixing of ammonium chloride is still a spontaneous process. I just told you that exothermic process are spontaneous. Why is an endothermic process spontaneous, even though it's an opposite process? Okay, it goes to show you that energetics, enthalpy is not the whole story. In order to define spontaneity, you need to look at everything. And one of the parameters in that equation is energetics, but another parameter is actually chaos. The system ability to get more chaotic. And that actually is the second law of thermodynamics. The second law of thermodynamics simply states that when a system becomes more chaos, there's more disorder, in other words, then that's going to be a more spontaneous process. Okay. When it becomes more chaotic, we say it has a higher degree of entropy. We call that chaos, entropy, for lack of a better term. Well, you find out later on that entropy is actually the availability of microstates. That will be the more formal definition. Okay, so entropy can be viewed as a measure of randomness or disorder. Okay, ink going into and mixing in water, it means that initially when it's a drop, it has a certain amount of order, but then when it disperses, you've got more randomness, you've got more chaos. So the entropy increases in that particular case. Okay, the entropy sort of increases in that particular case. So that's an example of entropy. Now, a guy by the name of Ludwig Boltzmann actually gave us an equation for entropy. You don't have to know where it originates, just kind of know the main factor of this particular equation. He basically said that S, which is a symbol for entropy, equals K, which is a constant. It's R divided by Avogadro's number times the natural log of the microstates. What are microstates? Well, microstates are telling you the available randomness for that system. Okay, so let me elaborate on that, but this is the equation for entropy. Okay, I won't ask you to apply this equation, but I just want you to know there is an origin to that equation. Okay, an origin to entropy, the equation of. So in any discussion of entropy, you have to look at the state of things to come, which is if you have a 52 deck card and you throw it in the air, it becomes random. Or just the progression of time, our history shows that things tend to become more chaotic, especially in time of war. Here you have nuclear spent fuel. And again, it's a dump site. You have greater entropy there. And of course, your room, probably right before midterm or right around the last week of May. You're going to find out that your room or your house, if you're the head of the household, becomes more chaos, just like my room here at my house. It's just a mess. Okay. And so that's a higher degree of entropy. And so the question is, well, if things always go towards higher entropy, why fight it? Why fight cleaning up your room when that's just what nature's intent? Well, that's because human beings tend to be a species of order. And so we like order. Maybe some of us don't, maybe some of us do, but we tend to like things organized. Okay. Anyway, let me go ahead and talk to you guys about microstates. So the best way to discuss this is if you play poker. Okay, I bring poker in this discussion because it's very relevant to entropy. If you play poker and you have 5 cards, then you know the highest hand is what we call the royal flush, which is this right here. And if you want to win in a poker game, then you have 4 chances, because there are 4 suits in 1,302,544 ways of distributing 5 cards when you have 52 as your container. Okay, so 4 hands in 1,302,544 is the chance of getting a royal flush. That means you have 1,302,540 chance of getting nothing out of 1,302,544. So what you see here is that the availability, the chances of getting nothing other than a royal flush is higher statistically. Okay, so that probably is the greater state of achieving rather than a royal flush. And so if you go to Las Vegas, then the chance of you getting nothing is much more enhanced than getting a royal flush. Again, that's just the law of nature. It's defined by entropy. So let's take a look at a chemical system. Okay, let's take a look at a 4-particle system like that. Let's say we have 4 particles in a chamber, and the chamber has two sides, and these particles are free to roam around. Okay, so there is a chance that all 4 particles are in one side. There is a chance that only one of the particle is on the other side, and 3 remains on the original side, or there's a chance in which there are 2 particles on each side. So the question is, what are the probability for these particular states to exist? Well, here's the probability. For all particles to be on one side, you have that one situation. For one of the particle to be on the other side, you have a 1 in 4 chance. You have 4 chances of that happening. But how about when 2 particles are in one side and 2 particles are in the other side? You have a 6% chance of that happening. So if you look at the distribution, okay, if you look at the distribution of occurrence, and now you flip these particles to the other side, this is basically what the probability of occurrence is. In other words, you have a greater probability of particles being evenly distributed in the both sides rather than the particles being distributed in one side or the other. So this is your greater microstate. that is going to be your higher entropy. That's the state that nature prefers. That's the state that nature prefers, okay? And that's what we mean by microstates. The available microstate is the availability that is going to be the more spontaneous process, okay? So let me go back. This scenario right here, it's not impossible, okay? Where all the particles are in one side and none of the particles are in the other. That's not an impossibility, but it's highly improbable, okay? So please keep that in mind. When you have not 4-particle system, but you have moles and moles of a particle system, then this distribution of particles in both sides is going to be higher. And so that's the chance that is the most likely event. Okay. Again, although not impossible, highly improbable for one side to be loaded with particles versus the other. And that's what we mean by microstate and entropy. Entropy states that these microstates are possible and that some have a higher degree of probability versus the others. Okay, more microstates, more states, larger entropy, more likely event. That's what we're trying to say with entropy here. Okay. Yes, we can reverse. We can reverse entropy with work. Okay, and what you will see is that we will reverse entropy when we clean up your room, but you also see that the second law of thermodynamics will state that entropy is always increasing in the universe.
Professor?
Yes.
Oh yeah. So I made that comment when you were talking about how Stephen Hawking was saying that if you went back in the universe, once the universe expanded, if it went back on itself, that would be reverse entropy. But in high school, I learned that entropy is all the time. So even if your room is messy and let's say you clean it, that cleaning is still creating more disorder because there's never going to be the more you do things, the more disorder, no matter what that is.
You're exactly spot on that. And it's pretty good that you're learning that in high school. You probably studied thermodynamics and you see that in our discussion here, but you're exactly spot on. It's the second law of thermodynamics. Just like the first law of thermodynamics states that you can't create or destroy matter, second law of thermodynamics states that entropy is always increasing. So you're right. Unless there's a rule in science that we don't know about, it's always increasing. Thank you for that comment. Okay. So again, going back to this, more states, larger entropy, more likely event. Okay. So let's take a look at concrete examples like a solid. Solids are highly ordered, so they have a high degree of organization. A solid will be in space X, Y, and Z in the coordinations, in a coordination, okay? And it tends not to move from one point to the other. So it's highly ordered. If we now heat that solid and melt it, so we have a liquid, they're still in close proximity to each other, but they're tumbling amongst each other. And so the entropy is greater because there's some more available states for that matter to go from one position to the other. But the entropy is still low compared to the last state. That is the gas state where things are not connected and everything's loosely held and everything's just bouncing around. So in terms of entropy, we can say that the solid has the lowest entropy followed by the liquid, and the liquid is much, much less than the gas, or the gas is much, much greater than the liquid or the solid. So we use this much greater sign, okay? By the way, there's actually a fourth state of matter, and that's plasma. And so we would expect plasma to have a higher degree of entropy. just based on the fact that now it doesn't have electrons. Matter, plasma is a state in which matter doesn't have electrons, and so we have that particular plasma state. It's very pertinent in the surface of the sun, not so much here on planet Earth, but it is pertinent in our plasma TV, okay? So let's take a look at third law of thermodynamics. Third law of thermodynamics simply states that when you have a pure chemical in its crystalline solid, it's got to be a pure chemical, meaning that it's got to have a pure element. It's got to be a crystalline solid. It's got to be a solid, in other words, and it's got to be at 0 Kelvin. Remember, the temperature has an absolute scale, and the absolute scale starts at 0 Kelvin, minus 273 degrees Celsius, minus 273. When we have that state, then that state has 0 entropy. Everything's highly ordered. So entropy, unlike enthalpy, remember we talked about enthalpy last time. We said that we can assign certain systems, certain chemicals, as 0 enthalpy because it's relative. We say that this is how we define it under standard state. We'll give that value an enthalpy of 0. In entropy, it's absolute. Okay, we have a 0 point when it's a pure crystalline solid, and we have 0 Kelvin. Then it has 0 entropy. It's highly ordered. That happens to be the second law of thermodynamics. And you guys remember the scientist responsible for discovering absolute 0. That was Charles in the gas laws. He basically took matter. He extrapolated what would happen to the volume if we reduce the temperature, and he found out that the volume would cease to occur, would have 0 at minus 273 degrees Celsius. And we define that now as 0 Kelvin. So that's the third law of thermodynamics. We have 3 laws that we're going to be studying. The first law is the law of conservation of energy. The second law is the entropy of the universe is always increasing. And the third law is about absolute entropy. That's what we are covering here. Okay. So let's go back to our original question, the second law of thermodynamics. In any spontaneous process, there is always an increase in entropy in the universe. Entropy in the universe is always increasing, as Ashley pointed out, okay? It is not conserved. In other words, it's not like the first law of thermodynamics. First law of thermodynamics tells you energy is conserved. You can't create or destroy it. We have a certain amount of energy in the universe, and it can be converted from one form to the other. That's outside of Einstein's equation, E equals mc squared. But looking at the first law of thermodynamics, energy is conserved. Second law of thermodynamics tells us entropy is not conserved. It's always going up. It's always going up. Okay, so this is the second law of thermodynamics as it is written in an equation. The change in the entropy of the universe is equal to the change on the entropy of the system plus the change in the entropy of the surroundings. And that is always increasing. It's always positive. It's always positive. Okay. But recall what we talked about last time. In any discussion of thermodynamics, when you're looking at the universe, there are 2 components of the universe, the system and the surroundings. Together, they make up the universe. And so if we're looking at the entropy of the universe, we have to look at the system and its surroundings. And so if one is negative, then the other has to make it up. The other one has to be so positive as to either the entropy of the universe is 0 or the entropy of the universe is positive. So, but it generally is never negative. It's never negative. It can be 0, in which case we have an equilibrium process, but it's mostly just positive. Okay, so when the entropy of the universe is 0, there's no tendency for anything to occur. But when it's positive, and this is key right here, this is important because that leads to free energy, which is the topic that we're going to be discussing in the next section. Okay, so when the entropy of the universe is negative, then the opposite is the spontaneous process. Okay, the opposite is the spontaneous process. And again, remember that entropy, in terms of when we think about it in chemical systems and processes, it's about the available microstates, and that the available microstates means there are greater degree of randomness. Okay, so going back to Ashley's question or comment about if you clean your room, the entropy of the universe is still increasing. And that's so very true. The entropy of the universe is always increasing. Remember, when you look at your room or your house or your car or whatever you're looking at, then you are part of that universe. You are part of that universe. So the universe is your room, the system is you, and then the surrounding plus you, okay, is your room. So suppose we want to make the, well, it looks like the system here is your room and the surroundings is you, okay, according to what I have here in my slide. So we want to go from a very chaotic room to a very organized room at the end of finals, okay, over the summer. Maybe that's your summer project, or maybe it's spring cleaning. Well, Ashley said, you have to put in the work. You got to do some sweating, and you have to take in the food to get the energy to put in the work to organize your room. So the entropy of the universe is always increasing, no matter what, okay? The entropy of the room may be negative, but at the expense of you, okay? We do not violate the second law of thermodynamics. We do not violate that. So I just want to point that out, okay? So let's take a look at this right here. We're looking at, again, I remind you about the entropy and the chaos and the microstates available. So here we're just going to look at which condition for copper, 273, 295, 298, has a higher degree of entropy. For phases, sodium solid, sodium liquid, sodium gas, which one has a higher degree of entropy? For water, solid, liquid, and gas. For the dissolution of these chemicals, sodium chloride as a solid, or when it's dissolved in water, aluminum chloride in solid, or when it's dissolved in water. So I have a poll here, and it's a quick poll. It's a multiple choice poll. All you have to do is click on the answer. And I just want to get this discussion going. So I'm going to launch it. I'll give you guys a couple of minutes to answer this and see what you guys say. So you guys should be seeing the poll right now. I'm going to end this poll, and we'll see the answers here. Okay, so you guys should see the answers. Let me just make sure. According to the first one here, you guys pretty much, well, some of you said that 295 was a higher degree of entropy than 298. Okay, and you were probably not even reading the question. You were just picking the last one because that's how it's shown in the slide. I sort of mixed it up so that you actually had to read the question. And you will see that in when it comes to temperature, the higher the temperature, remember temperature monitors molecular motion. So if you have a higher temperature, the species, the substance is moving faster, it's vibrating faster, even if it's a solid state. And so it's going to have more available microstates because of its vibration. So at higher temperature, it's going to have a higher entropy. And here you see that, by the way, entropy is defined as joules per mole Kelvin. There's a temperature component in the unit of entropy, and it's defined as joules. Unlike enthalpy, which is defined as kilojoules per mole, okay? Entropy is joules per mole Kelvin. And that's important. Why? Because when you put the two parameters together and you have kilojoules and joules and you try and add them up, you're going to be off. You got to convert both units to either joules or kilojoules. I just want you to be aware because that's a common mistake that I see all the time in thermodynamics. You guys forget about the units you're using. Anyway, 12 out of 14 of you got this right. Okay, the higher the temperature, the greater the entropy. Let's take a look at sodium, and you can see that again, the gas state is going to have a higher entropy. And I think one of you said it was solid or liquid. Gas is going to be more chaotic. We just talked about that. And so it's going to have a higher degree of entropy. For water, again, it would be the gas state. For carbon, graphite, 5.7, 198. By the way, remember this super zero right here? This super zero means that you are at standard state. Standard state is not 0 Kelvin. Standard state is 25 degrees Celsius, 298 Kelvin, and 1 atmosphere pressure. So we're looking things at under standard state conditions. Of course, the gas state for carbon is going to have a higher entropy than the graphite. Now let's take a look at sodium chloride. In sodium chloride, we can see that when you dissolve sodium chloride in water, it has a greater degree of entropy. And that's because when sodium chloride goes into water, the water will go in, water's polar. The positive end of water is going to be attracted to the chloride ions and then dislodge it, okay? And then the negative end of water will be attracted to the sodium ions and dislodge it. And then you have the hydration process. Let me just let you think about that hydration process, okay? When you have sodium chloride solid, it's highly organized. When you have water by itself, it's somewhat organized. It is organized because of hydrogen bonding. When the water molecules now is attracted to the ions, okay, there is some degree of organization. Why? Because the dipoles of water has to be orientated correctly to the ions. And then when the hydration process occurs, the water molecules have to surround the ions. And so that's somewhat of an organized assembly of the water and the sodium chloride. But still, compared to the solid, it's got a higher degree of entropy. But take a look at aluminum chloride, okay? Aluminum chloride, we say, has a negative entropy, okay, for this particular. And again, we're looking at it versus some state, and it's got minus 148. And the question is, well, why is that? I mean, the water is going to be attracted to the ions as well. The aluminum chloride is going to be organized, and now it's going to be with the water. But you got to remember that the chlorides or the aluminum is +3. The +3 in aluminum dictates that the water become more organized in its orientation. So that lowers the entropy for that particular system. Okay, that lowers the entropy. And so we give it a negative entropy in terms of relative to, say, under standard state conditions. So think about that for a moment, and you can see that when sodium chloride dissolves, it's got an entropy of 115.1 joules per mole Kelvin, but when aluminum chloride dissolves, it's minus 148. It's pretty interesting. This is you need to remember that, especially for those of you in lab, because you will see a similar question like that in your activity, okay? Let's take a look at methanol. Methanol, you have the liquid versus the aqueous. Remember that methanol can hydrogen bond. It's not that much greater than the liquid state of methanol, just slightly higher by about 4 joules per mole Kelvin, but still the aqueous is higher in terms of that. Gas diffusion, when you go from oxygen and it's diffusing, you can see that aqueous, it's highly organized because it's in somewhat of a liquid gas state, but when it's in a gaseous state, that's why I said gas diffusion, it's got a higher entropy there. So these are just examples of not doing numbers, but just thinking about microstates available and seeing the relative entropy for systems. And then complexity. When all else fails and you have nothing else to compare, complexity is your go-to um, criteria for judging entropy. The more complex the system, the greater the entropy, because the more complex the system, the more microstates available. So when you're looking at elements, we're going to find out that elements with more subatomic particles like rubidium is going to have a higher degree of entropy than potassium, which has a higher degree of entropy than sodium, which has a higher degree of entropy than lithium. Okay. When all else, when you don't have anything else given to you, like the phases, okay, or the reaction process, then just look at the complexity in terms of the number of particles that particular system contains, and then judge the entropy based on that. But we do have values, and this is found in the back of your book, as well as the appendix of your lab manual, where we can calculate the entropy change for a system, okay? And it takes on the classic calculations of products minus reactant. And we've seen that already when we talked about enthalpy. When we want to figure out the enthalpy for a reaction, we look at the enthalpy of the products, multiply it by the moles, and we subtract it by the enthalpy of the reactant, multiply it by the moles, and that difference is the enthalpy of the reaction. It's always final minus initial, always final minus the initial, okay, when we're looking at changes. So I put X here because you're going to find out whether you're talking about enthalpy, delta H, entropy, delta S, or free energy, delta G. It's always going to have this products minus reactant type of equation in order to calculate its value for that reaction. Remember, these are state functions. State functions only depends on its final point and its initial point. Doesn't matter how you get there. Doesn't matter how you get there. So this is the equation you would use for enthalpy. This is the equation you would use for entropy. This is the equation you would use for free energy. Okay, so let's take a look at this particular example. We have beryllium hydroxide, and we have the decomposition of beryllium hydroxide to beryllium oxide and water. Without even doing the calculations, you guys should know whether the entropy is positive or negative for this particular process. Is it going to be more ordered in the final state, or is it going to be more disordered in the final state? And here you can see that we start out, this is a balance equation. We start out with one chemical and we end up with two chemicals. So what do you think the entropy will be, positive or negative? Okay. Hopefully, I should have put a poll question on this, but I forgot. You guys should know that because you have more states in the final product versus the initial, it's going to be a positive entropy without even doing the numbers. So that's a good way for checking your calculations. Is just use common sense. Okay, use common sense. You're going to see that, yeah, we have a solid, and then even more, we end up with a gas. So again, that is another indication, even though one of the co-product is a solid, the other co-product is a gas. The gas state is going to have a higher degree of entropy. So not only do we have more particles, the product is in a gas state, which is going to have a higher degree of entropy. So right away, we would say that the entropy for this process is positive. So when we do the calculation, this is the calculation right here. These are the entropy values in joules per mole Kelvin. So we need a temperature. We need a temperature to calculate these. And you guys will know how to do this. Yes, thank you, Jenny. It's indeed positive. Thank you. We do need a temperature because in order to remove the Kelvin, you need a temperature for that. Okay, generally, if you have super zero right here, then that temperature is 298. Okay, so remember that the mole ratio is 1 to 1 to 1. So when we do this particular problem, it's products minus reactant. And in this particular case, we would say 188.83 plus 13.7. Like I said, the math on these things are not difficult. Minus 50.21. And when you get the answer there, it's 152.39, positive 152.39. So the entropy does increase. Okay, these exercises, like I said, they're super easy. Consider them free points if you see them in an exercise. They're not difficult. I think the most difficult thing is reading the values in the appendix because they're so tiny. Okay, and make sure you pay attention to the phases, because if you find water, liquid, and this is the gas state, then you're going to be off. You got to pay attention not only to the chemical, but its phase, because in the appendix, they will give you the entropy or the thermodynamic parameters for water in the solid, liquid, and gas state. You got to find the one with the correct phase so you don't make silly mistakes. Okay. These type of calculations are so easy. Don't goof up by using the wrong value. Don't goof up by using the wrong value. So that pretty much takes care of entropy. Okay.